Hello everybody, in this video we are going to start the conversation about function transformations. Now even though our notes say linear and quadratic, we're also going to look at exponential functions. We're going to focus on identifying the parent function for each family and comparing lines that have been translated up, down, left, and right, and kind of looking at some of the key features that would allow us to apply and identify those translations. So let's go ahead and take a moment to talk about parent functions and vertical and horizontal translations. So let's talk a little bit about what a parent function is. So even though in this video and in this set of notes we're not going to focus on the equations, but more of the act of transformations such as moving something up, down, left, and right. The equations will also become very important to us to determine whether something needs to be moved to the left or to the right or up and down. So on the top you're going to see that this is the linear parent function. So a parent function is just the most basic equation in that function family. So just by having an x will create a straight line. If you start adding numbers to it, it will cause some changes, whether it's shifted up, down, left, or right, or the steepness and direction of the line. But essentially, if it has an x, then it's just going to be a straight line. And so it's going to belong to the linear parent function. But this one right here is the most basic of the linear functions. And this is the one that we're going to constantly compare other functions to. Now, this h right here represents a horizontal translation. Number one, notice that it's inside of the parentheses with the x, and that's going to tell us whether the line is going to be shifted to the left or shifted to the right a certain number of units. Notice that the one down here at the bottom, we have a k. That k is not located inside the parentheses, it's actually on the outside, and that k represents if we're going to take our graph and shift it up or shift it down and how many units. Now, once we start talking about the equations, we'll focus a little bit more about where the number is, if it's positive, if it's negative, and what that actually does to the graph. But for this video and this set of notes, we're just going to look at graphs that have been shifted up and down and comparing them to the parent function. So let's go ahead and talk and graph the linear parent function. So I'm going to actually take the linear parent function and I'm going to rewrite it as y is equal to x. And I'm also going to create a table so I can list values and graph this out. So when you see the linear parent function, you're going to notice that whatever your x's are, your y's are going to be the exact same thing. So I'm going to use some positive and some negative numbers to create a graph on both sides of the x-axis. So I'm going to start with -3, -1, 0, 1, and 3. Now, one of the things that I want to point out, there's nothing special about these set of numbers. I just picked some numbers that were negative, I picked 0, and I picked some positive numbers to kind of get a general idea of what the entire graph is going to look like. So because this says that y is equal to x, that means that if x is -3, so is y. So I'm going to go ahead and graph this. -3, 1, 2, 3. And if x is -1, so is y. So -1, -1. If x is 0, so is y. 0, 0 is right here. You're going to notice that all your parent functions, no matter what family it belongs to, it will always go through 0, 0. All right, we have 1, so y is also 1, so we have 0.11. And then 3, 3 would be here. So let's go ahead and connect these dots, and we're going to label it f of x. So we're going to call all our parent functions f of x. And then we're going to call all the other functions or graphs that we create something else. All right, so notice that I have the linear parent function. It is a line Notice that it goes through the origin and it has a positive slope. This is going to be the template that we use and we compare to. This is the original graph before any changes have been made. Now, with that being said, there is one transformation that I do want to talk about, which is a reflection. So we are going to take the parent function and we're going to reflect it across the x-axis. So how do we reflect something across the x-axis? Number one, identify where your x-axis is, which is right here. Notice that we have very specific points here. We are actually going to measure how far each point is from the x-axis, and then use that same measurement in the opposite direction. So let me show you what I'm talking about. I'm going to start with this one down here. And I notice that this point is 1, 2, 3 units away from the x-axis, and it is below the x-axis. So the opposite would be to do 3 units above the x-axis. So here's my x-axis, and I'm going to count 1, 2, 3, and create a new point on the opposite side. But notice that they're still on the vertical line, but in the opposite direction. So when I look at this point right here, I notice it's 1 unit below. So my new point would be 1 unit above. Now, I have this point on the x-axis. It's just going to stay there. And I'm going to use it as part of my new line. So if it's on the x-axis, we're just going to leave it there. All right, notice that this next point is 1 unit above. So that means my new line is going to be 1 unit below. Same thing with this one. This one is 3 units above. We're going to count down 3 units. And that is enough to create my new line. So I'm going to go ahead and create this line. So one of the things that you're going to notice here is this is what a reflection across the x-axis looks like. The x-axis is our mirror, and everything that was on this side was moved in the opposite direction, and everything that was on this side was also moved in the opposite direction, and it caused a reflection. So for a reflection to take place, it basically changes the direction of your line. So for this one, we're going to make a note to ourselves, and we're going to call this g of x, and we're going to say that g of x is a reflection across the x-axis. All right, so notice that I wrote that g of x is f of x reflected across the x-axis. Now, the next thing that we're going to talk about is translations. Translations is the same thing as slides or shifts. So that means we are not changing the shape. We're not changing the direction of the line. We're not doing anything to the line except for moving it either up, down, or left or right, depending if it's horizontal or vertical translation. Now, in order for us to be able to do this, notice that we have our parent function that's already here. So we're going to start with this one, and I'm just going to go ahead and label that f of x. This is the parent function. This is the one we're going to compare it. We also need the points on this line to be able to create a new line that's either shifted left or right. So I'm going to start with the origin. I'm going to use this one. I'm actually going to circle the origin because that's the one that's going to let us know which direction this line is moving in. All right, so from here, I'm going to pick a couple more points. I'm going to pick 2 more points, and there is nothing special about the points that I am picking. Okay? I just need points on both sides of the line, and you can pick any of them or all of them that you see on here. Okay? So for this one, I'm going to ask you to shift the parent function 2 units to the left. So how do we create a new line that is shifted to the left? Well, you're going to take the points that we just pointed out, that we just set, and we're just going to count 2 units to the left. So for this one, we're going to go over 2, 2, 2, and since this one's on the x-axis, I'm going to go ahead and circle it, and then this one 2 and 2. Notice that I have created a brand new line. Let's go ahead and connect these dots and label it g of x because we have created a whole new line. All right, as you can see, I have my g of x, And I went ahead and wrote in that g of x is just f of x, translated, shifted, moved, whatever word you want to use, 2 units to the left. How do we know it was moved 2 units to the left? Well, look at the x-axis and notice that this x-intercept is 2 units to the left of the original parent function. So what if I ask you to take the parent function and shift it 4 units to the right? We're going to do the exact same thing. I'm going to take the original points that I have here, and instead of counting 2 to the left, we're just going to count 2 to the right, and it's going to create a whole another graph. So for this one, I don't have enough room to go 4 units to the right, but this one does. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Last one. 1, 2, 3, and 4. Notice I have created a whole separate line. Let's go ahead and connect those dots. We are actually going to give it a different name because it is different than g of x and f of x. So we're going to call this one h of x. All right, so as you can see here, I'm going to go ahead and circle my x-intercept, and I can clearly see that h of x is the same line as f of x, but it has been moved, shifted, translated 4 units to the right. Why? Because the x-intercept is 4 units to the right of the parent function. So I can see by comparing the x-intercepts which direction my new line is in. Now, we can do the exact same thing by taking the parent function and shifting it up or down. So I'm going to actually do this one a little bit quicker, and I'm going to pick either the same points or different points. It doesn't necessarily matter which points you pick as long as you pick some in both directions. So I'm going to pick these ones right here. Notice that I circled my origin, and then we're going to shift this up and down. So I'm going to create a graph that has been shifted 3 units up, and let's do 3 units down. Okay. So as you can see, I went ahead and graphed a new line, g of x, that is located 3 units above. So I basically took all these points and counted up 3 units and created a brand new line. I did the same thing with h of x, but instead of going up, I decided to go 3 units down. So from here, I took each one of these points, counted 3 units down, and created a whole new line. And if you're trying to identify whether it was translated up or down, we're going to compare not the x-intercepts this time, but the y-intercepts. The y-axis is what lets us see if it's above it or below it and how many units. The x-axis lets us know if it's to the left or to the right and how many units. And so that is what vertical and horizontal translations look like compared to the parent function. I'm actually going to stop right here, and in the next video we're going to do the same thing but with a quadratic function. So I hope this helps, and I'll see you guys in the next video.